right? So counting seems silly, right? Like we're going to learn how to count. Let's talk about that a little bit, all right? Yeah. One. Two. I can't believe you guys would know that. You're too young. That's from like the 70s, man. So number one, counting is hard, right? It doesn't seem like it, but you'll see. All right, and we're going to talk about the product rule. We're going to talk about the sum rule, the subtraction rule, which is also known as the inclusion-exclusion rule, then tree diagrams, the pigeonhole principle, and why do we care about all this stuff, right? We're going to talk about all that stuff today. There's also a division rule. We're not really going to get into that today. We'll see that in action a little bit later, but we're not going to deal with that today. So counting is hard, and I'm going to prove it right now. How many people are in this room? How many? 6? I was taking a guess last night when I made this. So that wasn't too hard. All right, let's try another one. How many fingers am I holding up right now? 11. Just people watching this video are going to wonder, how did he do that? Hold up 11 fingers. Yeah, easy enough. You can count the fingers, right? Okay. All right, how about this one? How many push-ups can Chuck Norris do? All of them. That was a little harder to count. All right. So these kind of questions are simple, right? This is the kind of stuff we probably think about when we think about counting. Well, we're going to look at some trickier questions here. For example, how many bit strings of length 7 are there? Right? That's a tricky one. I'm not going to answer that right now. We will answer it today, though. How about this one? How many variables can exist in a given program? Right? Like the Java language, for example. If we know what the rules of the variables are, they can have numbers and letters and certain symbols and so forth, and they can be X amount of characters long. How many variables can you create, right? This one, you may not even know this term. You should, but how many nibbles can exist with no consecutive ones? Anybody know what a nibble is? It's half of a byte. Yeah, it's a real term. I'm not making that term out. It's a real term. You know what a byte is, right? B-Y-T-E, it's 8 bits. Well, nibble is 4 bytes, or 4 bits, I mean. It's half that. It's just a programmer being clever, right? Whoever came up with that term. It's part of, it's almost a byte, it's a nibble. But how many of those can exist with no consecutive ones in a row? In other words, 1, 1, 0, 0, that one is not what we're talking about because it's 2 ones in a row. 1, 0, 0, 1, that's one of them, right? How do we count that? We'll talk about that later. How about this one? How many 6, 7, or 8 character passwords can exist under the following conditions? Every character must be a letter of the alphabet or a digit, and every password must have at least 1 digit. How many passwords like that can exist? How do you count that? It's not a matter of just going 1, 2, 3, right? No. Much trickier. So let's start with some basic foundational stuff here that ties into how we can learn how to count properly. And the first one's the product rule. And the idea is this: if a procedure can be broken down into a sequence of 2 tasks, and one task takes m number of steps, and the second task takes n number of steps, then the procedure takes can be done. That's a typo. I'm not fixing it either. But the procedure can be done in m times n different ways. All right? That's the product rule. Now that's very somewhat abstract a little bit. Let's take a look at some examples to make sure we understand what's going on here. And these, you kind of know these intuitively, I think. Some of these are easier to see than others. So a new company has 2 employees, Beavis and Butthead. They're partners, they're starting up this company. And there are 12 offices in the building. If Beavis and Butthead each get assigned to their own office, then how many different ways can they be assigned an office? You see what the question is? There's 12 offices. I put Beavis in office number 1, then Butthead could be in office number 2 or 3 or 4 or 5 or 6. But what if I put Beavis in number 2? Then Butthead can be in 1 or 3 or 4 or 5, right? There's how many combinations, how many ways can you do that? So what are the tasks, right? We're talking about this can be broken down to 2 tasks. What are the 2 tasks?
Where Beavis can be and where Butthead can be.
Yeah, assigning an office to Beavis and assigning one to Butthead, right? Very good. All right. How many ways are there to do each task? Well, this is the very first sort of basic principle of this counting stuff and with the products rule. How many ways are there to do each task? How many ways are there to assign an office to Beavis? 12, all right. How many ways are there to assign an office to Butthead? Yes, it's 11. It's 11, okay? Very good. Now, here's why it's 11. These are my 12 offices here. Let's decide that Beavis gets that office, right? Well, now, one of the offices is not an option for Butthead. Now, we could have used Butthead first, but either way, one of them would be 12, one would be 11. Since we're dealing with multiplication here, it doesn't matter if Butthead's 12 or Beavis is 12. Ultimately, the number of ways this can be done will be 12 times 11. Everybody see that? Okay. So the green ones are options for Butthead. And thus we can see there's 12 times 11 or 132 ways that these offices can be assigned. 132 different possible ways that this could happen, right? So just to make sure we're wrapping our head around this is the only time I'm gonna detail it like this for the rest of the day. I just want you to see it in this one scenario, okay? We're labeling these offices 1 through 12 like so. And right now, Beavis is in number 7. So Beavis is number 7. Butthead could be in 1 or 2 or 3 or 4 or 5 and so on, right? Or we can move Beavis to office number 1, and then we have Beavis in 1, Butthead in 2 or 3 or 4 or 5, etc., right? So you can see with every single place Beavis there's 11 other places that Butthead can be. That's huge. It's a lot of different combinations. I need to be careful with that word combination. That has a very specific meaning in discrete math. So, and I may inadvertently use it the correct way or the incorrect way. So I'm gonna try to censor myself and try not to use that word until we learn what it really means, okay? All right, so questions about that first problem there. We okay with this basic premise here? It's pretty straightforward, and when you put it in these fancy words that if there are n number of ways and m number of ways, and you multiply them together, that's somebody, right? We need to see it in action. Bless you. Okay, chairs in a banquet room, another typo that I'm not fixing, need to be labeled with an uppercase English letter followed by a positive integer not to exceed 100. For example, B29, right? Sounds like a bingo number. If every chair in the room is to be labeled differently from all other chairs, what's the largest number of chairs that can be placed in the room? Okay, so this being the case, the room is infinitely big. The question is how many chairs that can have a unique label on them, right? And let's think about what we're talking about here. It's B1, or A1, A2, A3, A4, A5, A6, A7, A100, B1, B2, B3, right? Get the idea? So what is it? What's the,
2,600,
what is it?
2,600, 26 times 100.
Yep, and yes, yeah. For some reason I was thinking it was 26,000. But so my head I did the math I was off by 1 0. Did everybody see why that is? So you're correct, that is the right answer. What's the tasks though? What are the tasks?
26 letters in the alphabet, 100 possible numbers.
Yeah, so the two tasks are one, assigning a letter to the chair, and then assigning a number to the chair, right? Those are the two tasks. Now keep in mind, you can do more than two tasks, right? There's not some rule that says you're only limited to two possible tasks, right? Maybe we also wanted to throw in there a character, right? Like an underline or a dash, and you wanted to know all the possible ways you could do that. Well, that'd be a third thing, right? The product rule will hold for that as well, okay? But we're just using two because it's easy to see, right? So we give the chair a letter and a number. How many times can each task be done? As we pointed out a second ago, 26 for the letter and 100 for the numbers, right? Make sense? So the final answer is 2,600 chairs, okay? Good? Pretty straightforward. This is pretty intuitive overall. This is stuff you kind of know, but it gets trickier as we move along, okay? This is foundational stuff. Did I hit the right button? Yeah, okay. Next question. The computer lab here has 32 computers in it. Each computer has 6 USB ports. How many different USB ports are in the computer lab? So, and the answer obviously is 32 times 6. I think that I don't need to explain that to you guys. I think you understand that. And if I were to ask you that before today, before we talked about before you took this class, I'm pretty sure you'd been able to answer that with exactly that math, right? What I want to show you today is not how to do 32 times 6. I think that's pretty obvious. What I want to show you is to make sure you understand, the answer is likely obvious, 32 times 6. What are the tasks, though? That's what I want to make sure we understand. Because when these problems get bigger and bigger and bigger and you want to use this method, you need to see what the tasks are so you understand what you're doing. So what are the tasks? Pick a computer and then pick a port, right? Yeah, makes sense? Pick a computer, picking a port, okay? So again, simple, but it's foundational to this counting stuff, all right? And these kind of problems, it's important to be able to recognize what are the tasks, all right? So let's take a look at this one we talked about a minute ago. This one's a little trickier. How many different bit strings of length 7 are there? First of all, what is a bit string? Yeah, just a string of ones and zeros, right? And we're talking about one that's 7 digits long, right? Okay, so this uses an extension of the product rule. We'll be doing a task choosing a 1-bit or a 0-bit multiple times, right? Okay, so the task is just choosing a bit. That's it, just one task. But we're gonna do the same task again and again and again. That's slightly different, right? With the ports and the computers, one task was picking a computer, one task was picking a port. In this scenario, this is one task, pick a bit. But I'm gonna do that task 7 times. Follow, right? So these are my 7 slots for the bits. So how many bits, how many possible numbers can go in the first slot there? 2, right? Okay, how about the next one? 2, right? Get all the way through, right? I'm not gonna bore you with making it change every time. So this ends up being 2 times 2 times 2 times, right, all the way across, or 2 to the 7th, which is probably the number you know, or the formula you know when you learned how to convert to binary, right? You probably learned that. But this is why that's the case, because of the product rule here, okay? So there, as we pointed out, there are 2 times 2 times 2 different lengths, bit strings of length 7, which is 128, right? And that's, I think that's what you said, Craig, right, 128 a second ago? Yeah. All right, makes sense? Again, this is stuff you've probably seen, but kind of understanding how the counting works comes in handy down the road. How about this one? How many different license plates can be made with the following conditions? Each plate has 3 uppercase English letters in a row, so AAA or something like that. Following the 3 letters, there are 3 digits in a row, so AAA, 1, 2, 3 or something like that. And then there's no prohibited sequence. So how many possible license plates can be made? That's the question. So how do we approach this task here? I revealed that too soon. I'll leave that on the board. How do we approach this? Well, you kind of, right? There are 2 tasks. We're gonna do one task 3 times, and we're gonna do the other task 3 times, right? Like the one before where it was just pick a bit, we did the same task 7 times, right? Before that was we had 2 tasks, we only did once, right? We picked the computer, we picked the port, and we multiplied them together. We could do, there were 32 options, and there were 6 options, right? And the task before this with the bit string, it was one task that had 2 outcomes, and we did that task 7 times, okay? There were 2 ways to do that. In this case, there are 2 tasks, right? And we're gonna do, and each task has some number of possibilities, which we'll see in a minute. And each of those tasks are gonna be done multiple times. Bless you, make sense? So with that in mind, what goes there?
An English letter.
Yeah, so how many possible ways can I get an English letter? 26, right? So task number 1, pick an English letter, right? And there are 26 ways to do that, okay? Task number 2 is gonna be picking a digit, which we're just not to task number 2 yet. We haven't gotten there yet, right? We're gonna do task number 1 again, right? So what goes there? It's again, 26 different ways to do that. And then again, 26 different ways to do that. So that's task 1, picking a letter. There's 26 ways to do it, and I did it 3 times, okay? Next up, and so you could say that it's 26 to the third, just like we did with the 2 to the 7th a minute ago, okay? But same thing, 26 times 26 times 26. Now, the 4th digit here, the 4th block in our license plate, what goes there?
A number, 10 possible.
Yeah, there's 10 possible, so our second task, right, is to choose a digit, 0 through 9. So there are 10 choices there, and then 10 choices in those, right? Multiply all that out, I think I did the math there, yeah, look at that fancy effect right there. And that's the final answer. To the whiteboards. Now with these kind of problems here, the goal isn't, today anyway, isn't do the hard math, right? That's just use a calculator for that stuff. What I want to know is, can we understand how to get to what numbers I do need to multiply together, right? That's the basic goal for today. So let's look at this first one here. How many telephone numbers are possible under the following conditions? And the first digit of the area code can be anything from 2 to 9. First digit of the 3-digit prefix can be 2 to 9, and the rest can be 0 to 9. So the first one, there's 8 possibilities, right? And then that's bullet point number 2. Bullet point number 3 is where that second 8 is, also 8 possibilities there, agreed? So we did the one task of picking a number from 2 to 9 twice, right? All the rest of them can be 10. We did that task 8 times, picking a number through 10 different options. Multiply all that out, and that's the number to get, right? Okay? The second one, this is what the rules used to be back in like the 60s. They had it a little bit different. So the first digit of the area code could be the same, 2 to 9, but the second digit could only be a 1 or a 0. That was it. All area codes had a 1 or a 0 in the middle. I'm not sure why that restriction, what the intent of that was. The calculation is pretty straightforward. I think you guys figured this out, that we can put an 8 there, or we can put 8 digits there, we can put 2 digits there, we can put 8 digits in those 2 spots, right? The first and second digits of the 3-digit prefix, and then the rest of them could be 10, right? You do the math and you get that number right there. I think you guys got that, okay? We good? Feel good about that? Let's look at the sum rule. The sum rule is if a task can be done either in n number of ways or in m number of ways, then there are a total of n plus m ways to do the task. Now, the product rule, I feel that we saw that it's pretty intuitive. When you see this one, you're gonna be like, duh, that's even more intuitiver, okay, for sure, all right. That's a real word, made that up. All right, so take a look at this example. There are 37 math faculty members. There are 83 math majors who are not faculty members. One of the above people will be chosen to be a member of a committee for the school. How many candidates are there?
120?
Yeah, 83 plus 37, right? Pretty obvious, okay? Not too complicated. I promise, this stuff gets more intricate than a little bit later. A lot of the stuff that we know intuitively, it's important to understand why it works, how it works, and then where are some more complex places where you can apply it. And we will see some complex examples in a little bit. All right, what are the tasks in this case? Ultimately, we're just doing one task, right? We have 2 ways of doing the one task. Does that make sense? Okay? We can either pick from this group or we can pick from this group. We're not doing both, because ultimately we need one candidate, right? One candidate. So there are 37 ways to pick that candidate, or there are 83 other ways to pick that candidate. But it's still one task, just picking a committee member, okay? And again, it could be one of 37 or one of 83. And this obviously can be extended to more than 2 tasks, right? I think that's pretty obvious, okay? So, for example, you've decided to perform a magic trick for class. That's right, you guys, not me today. There are 3 categories of tricks you know how to do: cards, coins, and illusions. You know 23 coin tricks, 15 card tricks, and 23 coin tricks is too many, by the way. 15, not enough card tricks. And 14 illusions. How many different ways are there to choose a trick to perform? There's 52, right? In other words, I'm just simply asking, how many tricks do you have to choose from? Right? And I know this is simple, guys. I do, I get it, okay? I don't want to insult your intelligence. But just making sure we understand these principles is important. So I'm just asking, how many tricks do you have to choose from? Well, I know this many coin tricks, this many card tricks, and this many illusions. That's how many I have to choose from, right? Add those up and you get 52. Now let's look at some more complex stuff here. How many possible variable names exist in the classic programming language BASIC? Imaginary bonus points if you know what BASIC stands for. Anybody remember? It's an acronym. Beginners, all-purpose, symbolic, instruction code. It's an old language from the 70s and 80s, stuck around into the 90s. And then Visual Basic, that was a thing, which is kind of ridiculous. But Basic's cool. I used to program in Basic years ago, like 30 years ago. Maybe more like 35 years ago, man. I'm getting old. Okay, here are the rules of one version of BASIC. There are lots of versions out there, but this is one of the rules of the version of BASIC. The variable name can only be a maximum of 2 characters long, right? So AB, or it can just be A or something like that. Each character can be a digit or a letter of the alphabet. Language is not case sensitive, so that means an uppercase A or a lowercase a are the same thing. All variables must start with a letter, not a digit. So you can't have 1B as a variable, but you could have B1, okay? And then the variable name cannot be any of the following reserved keywords. Those 5 words: by, do, if, and go. So you can't have a variable called go, right? Makes sense? So that's well, I want to know how many different variables can be created with those restrictions. That's the kind of question we're answering. So how do we approach this? This is a little bit trickier. What are some thoughts? I want to kind of have a little mini brainstorming session for a second. So the first character can only be 26 possibilities. Then the second character can only be 36 possibilities, right? The 26 letters and then the 10 digits. Is that everything?
Subtract by 5.
We have to subtract out those 5, okay? Is that it? Look at the first bullet there. Maximum, right? So it could be 1 digit, right? It could just be the letter A or the letter X or whatever, right?
Would we do 26 times, would it be plus 26?
It would be.
Yeah.
Yeah, very good. So we're looking at 2 different scenarios here, right? We have 2-digit variables, or 2 character variables, and then 1 character variables, right? As we figured out, that first number would be, there's 26 possibilities because it cannot start with a digit, okay? It has to start with a letter. And then, of course, there are 36 possibilities here because it's all 26 letters of the alphabet plus 10 digits, right, 0 through 9. So there's those 2, which we're going to multiply together, okay? And then we have, that's our answer for that, 936. And then this one, there are 26 possible things that we can start with here, right? And that's just 26. So if I add 936 and 26, forget about those 5 keywords for just a minute, but if I add those 2 together, that's the possible number of variables I could create, right? So that's the product rule and the sum rule, okay? Now let's think about what's happening here. The product rule says if there are 2 tasks and one can be done M ways and the other can be done N ways, you multiply them together. And then the other one says, the sum rule says, if a task can be done M ways and N ways, you add them together. So this task of, let's simplify it, saying creating a variable, well, it can be done one way and another way, right? 2 different ways. So we add those 2 ways together. As far as the individual task for creating the variable, it's just picking a character, right? And that picking that character can be done 2 different ways, 26 ways and 36 ways, 2 different types of, or 2 different ways to pick that character, right? So we add those numbers together, which gives us, look at all these theatrics with no answers, 962. But we do have those 5 variables that, if I were to, that 962 includes a variable called by and do and if and so forth. And so we need to subtract those guys out, and that gives us 957, okay? Make sense? So it's a little bit trickier. It's not super hard, but it's a little bit more involved. That's our final answer right there. Now, this is one of our questions that I had on that page that said trickier questions earlier today. How many 6, 7, or 8 character passwords can exist under the following conditions? Every character must be a letter of the alphabet or a digit, and every password must contain at least one digit. So how do we approach this one?
So there's three different ways we can do it.
Yep, there's three different ways we're gonna add up however many 6-digit passwords there are, how many 7 ones, and however many 8 ones there are. We're gonna add those together, right? So we just need to figure out what those numbers are. What's the 6, what's the 7, what's the 8, right? Okay, so that's a good starting point. Figure out all the 6, 7s, and 8, and then we're gonna subtract out ones that are not allowed is how we're gonna approach this, okay? Which ones are not allowed? Not the number, but what kind of password's not allowed?
Ones that don't contain a digit.
Ones that are all alphabets, right? Those are not allowed, okay. So here we go, we have the 6, the 7, and the 8. What's gonna go there? Okay, 36, good. How about the next one here? So they're all 36 for the moment, right? We're gonna figure out all the possible 6 combinations that can exist. Does that make sense? All of them. Later, we're gonna subtract out the ones that can't exist. All right, so what about that?
36.
Yeah, you guys got the idea here, right? Okay. And then the last one's the same thing, okay? So 36, we're gonna multiply, it's gonna be 36 to the 6th plus 36 to the 7th plus 36 to the 8th, whatever the heck that is, right? Okay? So let's just remove all that stuff on the left, and now let's look at, that's what we start with. We're gonna add those 3 together, but we need to subtract out this new stuff here. So what's next here? What do we subtract out of this? What's the first question mark? What's any of those question marks? Yeah, it's 26, right? Because if I multiply 26 to the 6 and 26, let's just pick the first one, the 6 up there. 26 to the 6, what does that tell me? That is a password that is only letter. Now, I could put a digit in there, right? Do you agree? I could put the number 9 in there, but that's not what I'm not asking what am I putting there. I'm asking how many passwords can exist that are all A through Z, right? Well, there's 26 to the 6th of those, plus 26 to the 7th of those, plus 26 to the 8th of those. You guys agree with that? Okay? So there are those numbers. Now, make sense? Now, the final answers, what are those 3 added up together? Does everybody understand that? That makes sense? Okay? We add those up and we get whatever that number is. 2.7 billion, or trillion, 2.7 trillion, okay? We good with that? Feeling okay? That's the final answer right there. So any questions about that? There's a couple, a little bit more intricate ones. When we get into the permutations and combinations lecture on Wednesday, we'll see much more involved stuff. And that's where we get into questions, kind of like what Jason was asking earlier, where order matters or order doesn't matter, and depending on whether you're gonna do, you know, which one you're looking for. Okay, let's look at the subtraction rule here. If a task can be done in either n ways or m ways, then the number of ways to do the task is n plus m ways, that's just the addition rule, minus the number of ways that are common to both, right? That's our intersect in a Venn diagram, right? Our intersection in a Venn diagram. And if you look at it from a Venn diagram perspective, that kind of makes some sense, right? So let's take a look at sort of a weird example. Here is, it's A, the letter A represents ways to do a task. This is my set here. I can do it carefully, slowly, quickly, perfectly, or excellently, okay? Letter B represents other ways to do a task. Slowly, perfectly, uniquely, stupidly. Those are the ways I can do the task. Basically, I'm just saying how many possible ways are there to do the task? Well, what's the answer by looking at those 2 sets there?
7?
Yeah, 7, yeah. I could do it carefully, slowly, quickly, perfectly, excellently, uniquely, or stupidly. Right, slowly and perfectly are there twice, okay? So, and you pointed this out, the subtraction rule states that the number of ways to do a task is the, I just said it, cardinality, sorry, the word slipped my mind, the cardinality of A union B. Well, what's A union B? It's all 9 of those together, right? That's A union B. But what's the cardinality of that? Remember when we deal with cardinality, we ignore duplicates, right? So the cardinality of A union B is subtracting out everything that's in both sets. Subtracting out one, just that number once, right? Okay, so in other words, this is the formula. A union B is carefully, slowly, quickly, excellently, perfectly, uniquely, stupidly. That's the union of the two. Agreed? What I want to know, what's the cardinality of that? Well, if you remember back to our days of cardinality a few chapters ago, chapter 2.6, I think, when you see the same thing in there twice, you only count one of them, right? So the cardinality of that is 7. Agreed? Remember those absolute value looking things, that's just cardinality. All right, so we good there? The formula for that is pretty straightforward. It's the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. Right, that's the formula. Dig it? Right, the cardinality of A is 5, agreed? Cardinality of B is 4, and then we subtract out the intersection, which is just 2. Okay. And that gives us 7. So let's take a look at an example here. How many bit strings either start with a 1 bit or end with the 2 bits 0, 0? All right? So what's a byte, first of all? It's an 8-bit string, right? So how many 8-bit strings can either start with a 1 bit or end with 0, 00? So knowing that this is a subtraction problem, where's our intersection going to be? What's our set A and our set B? Yeah, set A is anything that starts with a 1. What's our set B? Ends with 2 zeros. What's our set A intersect B? Yeah, it starts with a 1 and ends with 2 zeros, right? So we have to consider that in our calculation here, all right? So our approach is this. Figure out all the bytes that start with 1, that's set A. Figure out all the bytes that end with 0, 0, 00, and then figure out all the bytes that do both. Okay, so we're gonna look at 3 different things here. Add the first 2 and subtract the last one. Make sense? So we're gonna apply this formula here. That's how we're gonna figure out what the final number is, okay? And remember, whatever this number is, that we're gonna look at what is the cardinality of that set, that's A. Whatever this number is, that's the set B, we're gonna figure out its cardinality. And then whatever is in both, that's our intersection right here, we're gonna figure out its cardinality and subtract it out. Does that formula make sense? Okay? So let's take a look at this. This is an 8-bit string here, right? So let's find all the bits that start with the number 1. So what goes in each of these slots here? The first one will be only 1 because it's everything that starts with a 1, right? And that's choosing a bit, but you only have one choice, and the choice is 1. You don't have 2 choices, right? The rest of them will be 2 bits though, right? Make sense? So this ends up being 2 to the 7th, right? Because multiplying by 1 does nothing to it, right? All right, let's look at the ones that end with 00. What's that gonna look like? It's gonna be 2 to the 6th, right? 2 times 2, 6 times, and then the last 2 digits are just gonna be one choice, right? Make sense? That's 2 to the 6th, okay? All right, and then the intersection. What's that look like? Somebody said it, 2 to the 5th, right? Yep. So it's 1 followed by 5 2s and then 1 1. The reason for that is because the first digit, we're talking about that it does both, right? It starts with a 1 and it ends with 2 zeros. Well, there's only one way to start with a 1, right? And there's only one way for the second to last digit to be a 0, and there's only one way for the last digit to be a 0. So that's our final numbers there. We do the math on that, we get 2 to the 7th plus 2 to the 6th plus 2 to the 5th. Right? Now, are you able to, and this may be right now, it's simple. Down the road, it can be a little tricky. Are we able to see when should I add, when should I multiply? Are we seeing this? Is this making some sense? Okay. Now, obviously, in this case, what are we going to do, though? We already did the multiplication. That's 2 to the 7th, 2 to the 6th, 2 to the 5th. What's the addition going to be? 2 to the 7th plus 2 to the 6th. And then what else we got to do? Subtract out the 2 to the 5th, right? Good. Right? Like that. Okay? Those are the numbers there, and then we're just going to do the math where we add those first 2 and subtract the last one, which gives us 160. So the answer to how many bit strings either start with a 1 or end with 2 zeros is 160. Make sense? To the whiteboards. All right, so the approach on this is pretty straightforward. We're going to apply the same rule again. We want to just find the cardinality of A union B. Well, what's our A and what's our B here? What's our A?
Card magicians.
No, yeah, 220 card magicians, and then B is our 147. So the union of those two, if we were to just do the math on that, just add up how many things we'd see in the union, it'd be 220 plus 147. But if I want the cardinality of that, I need to subtract out the duplicates, right? Okay, so that's what our formula is right there. And so what is A? We just mentioned that, it's 220, 147, and the intersection is 51. So if we add up the 220 plus the 147, that's this part of the equation right here. Then that's, again, the cardinality of those. And then subtracting out the 51 right here, that gives us 316 magicians that are one or the other or both, card, coin, or both, right? 316 magicians. So, but that's not all, because my question was, how many of them are neither card nor coin? Well, that's the list of ones that are in one or both of those groups. So the next piece of that is then, there's 34 because we subtract 316 from 350. That's how many magicians are neither. Make sense? So again, it's not a super hard problem, but it is one you have to think a little bit harder about, right? Takes a little bit longer. Okay, any questions about anything we covered today?